Types of proofs. Now, the most common type of proof that we see is a deductive proof. That's basically like we were doing in geometry. Okay? That's where we've got known facts, and from the different facts we then deduce our conclusion. Okay, and then we saw inductive proofs. So method of induction. That one there is where we actually assume what it is we're trying to prove, and then we induce the solution. Another type of proof you may remember, we don't use it that often, proof by contradiction. And that's where we actually assume the opposite of what we're trying to prove. So whatever we're trying to prove, we assume the opposite is true, and then we work through and come up with some sort of contradiction. And once we have a contradiction, then we come to the conclusion, well, therefore my original assumption must be false, and so I can assume the other bit. Some techniques for when we're doing inequalities. This is a very common idea. If you've got to prove x is greater than or equal to y, a lot of times it's a lot easier to prove x minus y is greater than or equal to 0. Because showing something's always positive or showing something's always negative can sometimes be easier. So sometimes with these inequalities, first thing we do is move everything to one side and say, okay, I'm going to try and prove this is positive or negative, depending on the inequality. Okay. Here's, again, quite an old one. I want to prove PQ is less than or equal to P squared plus Q squared on 2. I'm going to change what it is I'm going to prove. I can move terms now. Right. And go, okay, I've got this statement, P squared plus Q squared on 2 minus PQ. And I'm going to try and prove this is always positive. Now, once I've determined what I'm trying to prove, then I can only use facts. I can't just move things around. So I get this statement, and on the top I go, okay, I'm going to make it all one fraction. The top becomes a perfect square. Well, that's always greater than or equal to 0. But I now know that is a fact. As this is now a fact, I can move terms. And so I can get that PQ and move it to the other side. And I've got what I want to prove. Right? So you don't start with PQ less than or equal to P squared plus Q squared on 2, I guess is what I'm saying, and then move the term and say, 0 is less than or equal to P squared plus Q squared on 2. If you want to move everything to one side, you just start with an algebraic statement. I'm saying nothing about its equality or its inequality. And I want to end up showing that that is always positive. Another way I could have done this problem. I could have assumed the opposite. This is a proof by contradiction. Probably not a normal way of doing it, but just to show you how it would work. So I'll assume the opposite true. I'm going to assume PQ is greater than P squared plus Q squared on 2. Now, because I've made this assumption, I'm assuming this to be true. So therefore, I can play around with it. If this is true, then 2PQ would be greater than P squared plus Q squared. Well, if that's true, then P squared minus 2PQ plus Q squared is, 0 would be greater than it. So 0 is greater than P minus Q all squared. Well, that could never happen. I can't square something and get something that's smaller than 0. And so there's my contradiction. Because we know P minus Q squared is always greater than 0. Can't be both greater than 0 and less than 0. Contradiction. So my original statement must have been false. Therefore, the opposite must be true. So, as I say, it would be an unusual way of doing that one. But, that's the technique. A squared plus B squared plus C squared is greater than AB plus BC plus AC. Way back in 1994, they've asked this, and it's appeared in many a trial paper since then because people just love it. They think it's the proof of this is just beautiful. So how do we do it? Well, I'm going to start with a fact. So therefore, a squared minus 2ab plus b squared is greater than 0. A squared plus b squared greater than 2ab. Of course, a and b were just random pronumerals. So I could have easily have done it with a and c. I could have done it with b and c. Add them all together. 2a squared plus 2b squared plus 2c squared greater than 2ab plus 2ac plus 2bc. Divide by 2, and we have our solution. A plus b plus c is going to equal 1. We're going to prove ab plus ac plus bc is less than 1/3. Well, I know a squared plus b squared plus c squared is equal to, so using our idea of, well, it originally saw it when we were playing with sum of the roots and that. So sum of the roots squared was equal to sum of the roots 1 at a time, all squared, minus 2 times sum of the roots 2 at a time. So basically it's that same thing. So a plus b plus c all squared minus 2 lots of ab plus ac plus bc. Now, we just proved that a squared plus b squared plus c squared is greater than ab plus ac plus bc. So therefore, a plus b plus c all squared minus 2 lots of ab plus ac plus bc must be greater than. Move it to the other side. I've also changed the inequality sign. Those 3 lots of ab plus ac plus bc will be less than a plus b plus c all squared. However, we've said a plus b plus c is equal to 1. Divide both sides by 3, and we have our result. We're now going to prove a third of a plus b plus c is always greater than or equal to the cube root of abc. So again, I'm back to a squared plus b squared plus c squared greater than or equal to ab plus ac plus bc. Move everything to one side. So I now know that's greater than or equal to 0. Now, I have multiplied by a plus b plus c. Now remember, a plus b plus c were distinct positive integers. So I've multiplied by a positive number, whatever a plus b plus c is, whether or not it's equal to 1 like in the last question, but it's always going to equal a positive number. So the inequality sign will stay the same, is what I'm getting at. If I wanted to expand the whole thing out, I get this wonderful expression. But look what happens. There's a whole heap of cancelling in there, and I've actually just got a cubed plus b cubed plus c cubed minus 3abc is greater than or equal to 0. So therefore, a third of a cubed plus b cubed plus c cubed is greater than or equal to abc. Oh, that's so close to what I want. Well, remember, a was just a positive number, we said. So I'm going to let a equal a to the power of a third, and b to be b to the power of a third, and c to be c to the power of a third. Right? Because if a is positive, a to the power of a third is going to be positive. If b is positive, b to the power of a third is positive, and so on. Substituting in, I get third of a plus b plus c is greater than or equal to a to the power of a third, b to the power of a third, c to the power of a third, and there's our result. This brings up this idea before you correct me. The idea is arithmetic mean is greater than or equal to geometric mean. Now, theoretically, you can only have 2 terms when you're talking about an arithmetic mean and a geometric mean, because what it's used for is to find the term in the middle of 2 other terms in arithmetic sequences and geometric sequences. And so you have 2 terms, average them, and you'll find the number in the middle that would make it an arithmetic progression. But if you find the square root of what they multiply together, you'll find the middle term if it was a geometric progression. But we often talk about it in n dimensions, and we still call it arithmetic mean and geometric mean. So if you've got n numbers and you add them together and divide by n, traditionally I guess what we call the average, that will always be greater than or equal to when you multiply all those numbers together and find the nth root. That idea can be very useful in solving inequalities. A lot of the time they might actually ask you to prove it. That in effect, if you have a look back at what we just proved, is what we just did for 3 numbers. Add 3 numbers divided by 3 is greater than or equal to the cube root of ABC. So we've just proved that result for 3 numbers there. Okay. Continuing on now from the last question. Suppose that 1 plus x times 1 plus y times 1 plus z is equal to 8. We're now going to prove x, y, z is less than or equal to 1. I think you're going to enjoy this little proof here. I know I do. 1 plus x times 1 plus y times 1 plus z. Expand it out and you get 1 plus x plus y plus xy plus z plus xz plus yz plus xyz. But we've just proven, and now we know arithmetic mean, geometric mean, a third of x plus y plus z will be greater than or equal to the cubed root of xyz. That would be true. So I could also say, when I multiply by 3, x plus y plus z is greater than or equal to 3 times. A lot of times it's more convenient to have the number on the other side. But as I say, they are just single things multiplied together. I could just as easily have done that. I've still got 3 things added together. xy plus yz plus xz. 3 things added together must be greater than or equal to 3 times the cube root of those 3 things multiplied together. So xy plus yz plus xz will be greater than or equal to 3 times the cube root of xy times yz times xz, which is, of course, x squared, y squared, z squared. Or the cube root of xyz squared. Okay. Oh, you're going to love it. Right, back to this. 1 plus x plus y plus z plus xy plus xz plus yz plus xyz. That's equal to 8. Therefore, that must be less than or equal to 8. Okay? Because I'm saying x plus y plus z is greater than 3 times the cube root of xyz. And xy plus xz plus yz is greater than, or equal to, 3 times the cube root of xyz squared. Now, I don't know if you can see it on the left-hand side, but look at what you got there. And if you can't see it, xyz I could rewrite as the cube root of xyz cubed. 1, 3, 3, 1. Power of 0, power of 1, power of 2, power of 3. That's 1 plus the cube root of xyz all cubed. And that's less than or equal to 8. So if that's less than or equal to 8, 1 plus the cube root of xyz is less than or equal to 2, which means the cube root of xyz is less than or equal to 1, which means xyz is less than or equal to 1. I told you you'd enjoy that proof. Did you like that? Okay, I'll show you an easier one then. I just love that solution. That's an incredibly long way of doing it, but I just love it. I wouldn't do it that way in a test. Cut too long. Okay, here's how I'd actually do it. But then, wasn't that just great? You had the 1, 3, 3, 1 pattern and the okay. Of course, we could just do this. Look, 1 plus x would be greater than or equal to 2 times the square root of x. Arithmetic mean greater than or equal to geometric mean. 2 things added together greater than or equal to 2 times the square root of them multiplied together. 1 plus y would be greater than or equal to 2 times the square root of y. 1 plus z will be greater than or equal to 2 times the square root of z. So 1 plus x, now I'm multiplying them together, by the way, I'm not adding them. Simultaneous equations where I multiply them. So 1 plus x times 1 plus y times 1 plus z is greater than or equal to 8 times the square root of x, y, z. So 8, because the condition was 1 plus x, 1 plus y, 1 plus z was 8. 8 is great. It's a little bit quicker. Just a touch. Well, if I showed you this first and did the other one second, you'd be going, what are you doing this for? Why are you doing that? All right, let's try another one. We're going to prove that we can trap this expression 2 on a plus b plus 2 on b plus c plus 2 on a plus c in between 9 on a plus b plus c, and on the right-hand side, 1 on a plus 1 on b plus 1 on c. Okay, again, I'm going to use the idea, arithmetic mean geometric. You'll be surprised how often we use this idea in these inequalities. A plus b times 1 on a plus 1 on b would be greater than or equal to 4. Okay? Anyway, we think, well, why on earth did I choose those things? And I guess I'm just looking at the question. I can say I've got 1 on A, 1 on B, but then I've got A plus Bs and so on. Because now I can say that. See, I had to work out how am I going to get an expression. Like the arithmetic mean and geometric mean was great, but it had everything in the numerator, not the denominator. Like if I wanted to say A plus B, it would be greater than or equal to 2 times root AB, but it's in the top. So how could I get it in the bottom? So that's where I multiplied these 2 things together. And now I can rewrite it. And I end up with something where I'm now saying, hey, these 2 things added together. The A and B are actually in the bottom of the fraction now. And it'll be greater than or equal to 4 on A plus B. So I now know that 1 on A plus 1 on B is greater than or equal to 4 on A plus B. So you may be seeing how the right-hand side of this inequality is now going to work. Remember, we're trying to show that, the 2 on the A plus B and so on. You see, because I could now say 1 on B plus 1 on C is greater than or equal to 4 on B plus C. 1 on A plus 1 on C is greater than or equal to 4 on A plus C. Add them together, and I get 2 on A plus 2 on B plus 2 on C greater than or equal to 4 on. Divide everything by 2, and I've proven the right-hand side. So 1 on A plus 1 on B plus 1 on C. So that's how I get the right-hand side. Well, what am I going to do for the left-hand side? Still going to use a similar idea, but I'm going to use all 3 terms rather than 2 of the terms. So now I'm going to get A plus B plus C and multiply it by 1 on A plus 1 on B plus 1 on C. Well, that's going to equal 3 times the cube root of ABC. Sorry, greater than or equal to. 3 times the cube root of A plus C, because the A plus B plus C will be greater than or equal to 3 times the cube root of ABC. The 1 on A plus 1 on B plus 1 on C will be greater than or equal to 3 times the cube root of 1 on A plus BC. They cancel, leaving me with 9. Hopefully you can now see where it's going to drop out. Because if I now rewrite that, I get 1 on A plus 1 on B plus 1 on C is greater than or equal to 9 on A plus B plus C. So there's the other half of the equation. So therefore, what I'm going to do is not quite what we want. If I'm going to replace A with A plus B, I'm going to replace B with B plus C, and I'm going to replace C with A plus C. Okay? There you go. Okay? So I ended up with 1 on A plus 1 on B plus 1 on C was greater than or equal to 9 on A plus B plus C. Fantastic. That's got my right-hand side is bigger than my very first thing. But I haven't got the bit in the middle. So how do I get it? Well, I change the bottom of the fractions. I don't want A, B and C as the single terms. I want A plus B, B plus C, A plus C as the bottoms of those fractions. So I just substitute them in for those pronumerals. And magic happens. The wonderful magic of mathematics. So therefore, we have our result. Oh, this must be an extra one I threw in. It's not on the sheet? Okay, we might want to write this one down. Well, the first bit I hope is straightforward. Again, if you use your arithmetic mean, geometric mean idea, the sum of 2 things will be greater than or equal to 2 times the square root of the product of the 2 things. And the A and the 1 on A cancel, and you get your result. A plus 1 on A is greater than or equal to 2. Okay. Another way I could have done it, I could have started with a known statement. I know that the square root of A minus 1 on the square root of A squared is always going to be positive. And so if I expand that out and then move the 2 over, again I get the result. That's another way I could have solved that one. Okay. Now we add a third term in, so C's in there now. We're going to show that B plus C on A plus C plus A on B plus A plus B on C is greater than or equal to 6. There's 2 ways I could have done this. I could have got 3 things, because I've got 3 things added together. The reason I didn't go that way, if I've got 3 things added together, it's going to be greater than or equal to 3 times the cube root. The number I want there is 6. So I'm thinking rather than doing 3 things, I'm going to do 2 things 3 times, and 3 2s are 6. That was sort of my logic why I've gone this way. Now, the other way I've done this, I've gone B plus A on A plus B. You probably didn't pick that one. Right? Because if I go B plus A on B and C plus A on A plus C and C plus B on B plus C, add them all together. So I now know that B plus A on B plus C on C plus C plus B on C is greater than or equal to 6. There's the magic number that I was looking for. Add the 2 things together that have a denominator of A. You have B plus C. Add the 2 things together that has the denominator of B, C plus A. Add the 2 numbers together that have a denominator of C. You've got A plus B. And bingo, you got it. Easily just have said arithmetic mean greater than geometric mean, so it's 2 times the square root of B on A times A on B, which is 1. So I see what you're saying. All right, try this one. Oh, he. Now it's the reciprocal. The single terms on the top, and the B plus C and the C plus A and the A plus B are on the bottom. Okay, so we just proved that. Okay, I'm going to let A equal B plus C, B equal A plus C, and C equal A plus B. How do we get that? It's not cheating. It's not cheating. A is just a number. Could have just easily said that it was B and C. It's made up by B and C. And so we end up with 2 lots of A on B plus C plus 1, plus 2 lots of B plus C plus 1, plus 2 lots of C on A plus B plus 1 is greater than or equal to 6, which makes 2 lots of A plus 2 lots of B, 3. Divide both sides by 2. There it is. All right, so I replace the A with B plus C, the B with A plus C, and the C. So I created the 3 denominators, if you like. Now, as I say, if it's confusing using little a, use capitals. And so replace capital A with little b plus c. And in your original one, have capital, and bang. Because it can get confusing, yes, having C's here. But hang on, that's the one I replaced. That's the one I didn't replace. And so on.